Thank you so much, Anna. Hello, everyone. Really happy to present this in front of everyone, and it seems like a turnout is really awesome. So really happy to do this. And if any questions come up during the session, feel free to post them in the chat. I'll try to answer them as soon as I see them. Yeah, if anything is unclear, do let me know. All right, so this session is about Winterfell. Winterfell is a Stark prover and verifier, and we'll get into that. But in terms of the overall outline, I want to give a very quick introduction to Starks, just to describe what they are, how they compare to other systems, other proving systems. Then this is not going to be like a deep dive into Starks, just a very high-level overview. And then we're going to do an overview of Winterfell, kind of what the library is, and some key features and things like that. And then we're going to build a post-quantum VGF. This is going to be kind of like actual coding exercise where I will, in real time, code up a post-quantum VGF using Winterfell. And then if we have some time, we'll also do another example, similar like walkthrough to demonstrate other features of Winterfell using Fibonacci, but Fibonacci example, but we'll see if we can get there. All right, so I'm sure a lot of people here are probably familiar with the setting. So when we talk about zero-knowledge proofs and proofs of computational integrity in general, there is usually a prover and a verifier, and they have some common function, and they have some input, some of which could be private, which is called a witness, and they have some outputs for this function. And then the goal of the prover is to convince the verifier that they've executed this function with these inputs and got the desired output. But the way they want to do this is, first of all, they don't want to send the witness to the verifier, but they also don't want the verifier to have to run the function in its entirety. So they do this by sending this proof, and this is the zero-knowledge proof. And the properties that we want to have with this is that we want the prover to run in kind of quasi-linear time. We want the verification to be as efficient as possible. Ideally in constant time, but logarithmic time is okay. Some systems have actual linear time. We'll talk about this a bit later, but ideally it would be at least logarithmic, or at most logarithmic. And then we want the proof size to be fairly small, and all of this is in the size of the computation. So the idea is that we can run this computation for maybe days or hours or whatever, and then the verifier can make sure that the computation was run correctly in milliseconds, checking a fairly small proof. And the exciting thing for me, at least, is that this f function f could be any Turing-complete computations. And obviously, some computations are more amenable to being efficient within zero-knowledge proofs. But in theory, at least, it could be any Turing-complete computation. And actually, in practice, it could be any Turing-complete computation, again, with some caveats. Zero-knowledge proofs really exploded over the last few years. The beginnings were laid in the 80s, but really, from practical standpoint, they become useful maybe in the last 5 years or so, maybe a bit more. This is just like a sampling of different proof systems and when they appeared, and there is a lot here and even more that I'm not listing here. But one of the things that I want to point out is that this proving systems all have their different properties. And there are a few properties that there are a lot of properties that we care about, that the few that I want to highlight here. One of these properties is transparency, meaning we don't need a trusted setup for the proving system to work. The other is succinct verifier. So on the previous slide, I said that verification time some proving systems could be linear. And ideally, we want to avoid linear systems. So if our verification time is logarithmic or constant, then we call this system to have succinct verifier. And then another property is post-quantum security, meaning even if elliptic curve cryptography breaks down, the system should still remain secure. So this is kind of like highlighting which systems fall where. This Winterfell is a Stark proven verifier, so I'm going to go a bit more deeply into the Stark system. But before going there, just showing this table, this kind of highlights some other properties and list different proving systems and kind of how they compare to each other. There are a lot of caveats to this table. There are a lot of nuance. So this is true most of the time, but maybe in some specific settings, this may not be true. But I think the overarching point that I want to make by showing a table like this is that there is no ideal proving system. There are proving systems that have small proofs, but they require, for example, trusted setups. There are systems that are transparent and fast, but they have fairly large proofs and so forth. So when I think about proving systems, I try to think about as I think about programming languages. That there are some proving systems that are suitable for specific use cases, but there is no kind of like ideal programming language, and there is no ideal proving system. At least with proving systems, we haven't come up with one yet. All right. Let's talk a bit more about Stark. Starks and advantages that they have as compared to some other systems. So first advantage is they're transparent and scalable. What this means is that there is no trusted setup and there is no pre-processing. So in many other systems, especially the ones that have very small proofs, you need to run trusted setup, and trusted setups are a pain. They're fairly difficult to orchestrate, and then you need to worry about whether they have been compromised or not. We've gotten much better now, I think, with running trusted setups. So there is less risk that something will go wrong, but obviously no trusted setup is better than even the best setup, in my opinion, at least. The other thing is that Starks use very lean cryptography, and this means they only require, from cryptographic standpoint, a collision-resistant hash function, and that makes them post-quantum secure because, as far as we know, at least quantum computers cannot break, or at least we don't know how to break hash functions using quantum computers. One other benefit, which is actually very interesting, is that they're fairly flexible. Like Stark proving system is very flexible in that it can work in many different fields. Even something as small as, like, let's say, 32-bit field is possible. And they have you can choose among very different trade-offs, and you can do it dynamically. So you can dynamically adjust the security level of a proof, for example, without changing underlying circuit definitions or anything of that sort. You can dynamically kind of change if you care about, let's say, proof size versus proving time. You can, if you want small proofs, for example, you can spend a bit more time generating those proofs and they will be smaller. But if you care about proving time, you can maybe tolerate larger proofs, and then your proving time will be smaller. All of this kind of works within bounds. You can go to extreme on any one of these dimensions, but you do have these trade-offs where you can choose. I think these trade-offs are fairly complicated with a lot of other proving systems where, for example, once you've chosen a security level, you can't easily reduce or increase it, or it's not trivial to how you would get a smaller proof or reduce the proving time by increasing the proof size or anything of that sort. Starks, the other advantage of Starks is in the specific settings, and we'll talk about them specifically when computations are uniform, they're extremely performant. The verifier, even in other settings, is also very fast. For most practical proofs, you only need single-digit milliseconds to verify those proofs, regardless of how long the computation was. The prover is very fast as well. I've given some benchmarks for MidenVM specifically. So on for example, on a single CPU core, you can prove around 10,000 cycles of MidenVM execution. And the nice thing also is that proof generation is massively parallelizable, meaning you can split it across multiple cores and maybe use GPU, FPGA acceleration, and all of that stuff. And it is a tough engineering challenge to scale it beyond kind of like, let's say, what is available off the shelves, but it is kind of not impossible to, in theory, run this in thousands of parallel threads and massively reduce proof generation time. As I mentioned, there is no ideal proving system, so there are some disadvantages that Starks have. Perhaps the most frequently cited disadvantage is the proof size. No matter what you do, you're probably going to end up with dozens of kilobytes for a proof. So even the simplest proof, something like proving a pre-image of rescue hash function, is probably going to be somewhere around 15 kilobytes. Maybe you can get it down to like 12 kilobytes with flexing some parameters. And on the upper side, like executing 1 million cycles of Maiden VM, you're probably going to be around 80 kilobytes. And then if you go beyond that, you could go depending on what the computation is. Probably, close like for the largest computations that I've ran, closer to 200 kilobytes. And I think beyond that, it's probably computations that are not very practical at this point in time. So if you think about proof size, it's probably somewhere between 15 and, for most practical computations, 15 and like 120 kilobytes, and maybe for some extremely large computations, it could go up to 200 kilobytes. Another kind of disadvantage is that, so far, at least, there hasn't been recursive starts. I think, and we'll talk about this a bit later, but recursion is definitely possible with starts, but it hasn't been yet demonstrated. And recursion is very important. So there are, I think, many people working on building recursive starts right now. So this will be solved, but at least at this point in time, there are other recursive systems out there, but starts haven't been made recursive yet. And then the other potentially complicating thing for starts is the arithmetization. Arithmetization is more difficult to work with than R1CS. I'll go into this in the next slide or next couple of slides, but basically, it is not as straightforward to work with, and especially build like standalone gadgets in AIR that can be integrated in other AIR and so forth. So that complicates and things and makes the learning curve for using starts much higher than in some other proving systems. All right. I mentioned this arithmetization here, so let's talk a little bit about what it is. So arithmetization is a kind of a step in building this proofs of computational integrity that takes a program that is written in some higher level language and reduces it to a set of polynomial equations, basically, or other statements about polynomials. This is true for most other proving systems as well, or at least many other proving systems. But for Starks, this is the arithmetization is called AIR. As I mentioned in the other slide, for other proving systems, a lot of other proving systems, it's called R1CS. And this arithmetization step is something that not all the people kind of immediately know what it is, but it is needed to build proofs. So let me take you through a fairly simple example of kind of arithmetizing a program. So let's say our program is something as simple as like this function that takes some input and a number of steps, and then what it tries to do is just like with every for every step, it just cubes the previous state of the variable or whatever input it got, and then adds 42 to it, and then after a while it returns this variable r. So basically, if you think about, you just initialize the variable to something, and then for n steps you cube it and add a constant to it. One of the things that we do in arithmetization first is what we call an execution trace. An execution trace is basically just kind of a matrix, but in this case, it's going to be just a single column. But basically, it's something that records the state of a computation at every step of its execution. So in this case, our execution trace is going to be fairly simple. We start with the initial value, so x0, the initial state of our computation, initialized to s. And then with every step, we take the previous value, cube it, and add 42 to it. And then once we get to the end, this is kind of our output. And we do this for n steps. Once we have the execution trace, and I would say kind of coming up with an execution trace for this computation is fairly straightforward, but if you think about more complicated computations, it becomes much less straightforward, especially for something like a program that is very complicated and has a lot of, like, let's say, branching logic, lots of loops and things like that. And we'll get to kind of like this uniformity of the program in a second. And the kind of taking it from execution trace to AIR is a set of polynomials that kind of like impose constraints over this execution trace. So what it means is that this equation should hold for all steps of the execution trace, or at least the steps that are specified there. So, for example, this relationship is something that is describes like how you transition from one row to the next. This equation describes what should be the first state, and this equation describes what should be the last state. And this basically is an entire kind of description of this simple computation. So this is what we call AIR. And AIR, by the way, I should have said earlier, stands for algebraic intermediate representation. So once we have AIR, then we can start generating proofs. But this is a crucial step, and frequently, again, this is very non-trivial of how you reduce a program to its AIR representation. And it's in many ways it is more art than science, I would say, at this point at least. All right. To compare, so I mentioned R1CS that is used by many other proving systems. Just to do a quick comparison with AIR and say why it is maybe a bit more difficult to work with AIR again. So both of them work over finite fields. I would say that AIR is well suited for uniform computations, while R1CS is probably better suited for some unstructured computations. Although you can do either with, you can attempt to do both with this, with either one of these approaches. It just, for example, trying to describe an unstructured computation with AIR is going to be very, very inefficient. On the other hand, trying to describe a very structured computation with R1CS, while it is possible to do that, you basically need to unroll loops and kind of represent within the circuit. So it's possible, but also probably not as efficient as doing it in AIR. So there are different types of computation. The uniform computation, again, I mean something that you have some kernel of a computation and you repeat it many times. If you need to repeat it many times, then the computation is kind of uniform, and many times could be thousands of times or millions of times. One of the important things or reasons why working with AIR is difficult is because composability is fairly complicated. Basically, because this uniform structure of a computation, if you have two uniform computations, it's not always trivial of how do you combine them together so that they still remain uniform. With unstructured computation, it's fairly easy. You can connect the circuits in fairly trivially, and you have a subcircuit and another subcircuit. You can connect them fairly easily. This is not the case with AIR. You need to think a lot, and maybe it breaks the uniformity in some ways where you try to connect to computation. So you need to work a lot to try to figure out how to combine them efficiently. I think this leads to compilation from higher level languages being fairly difficult for AIR as compared to R1CS. I know of a few projects that are trying to reduce higher level languages to R1CS, but I don't think there is a project even that is. I tried to do it at some point in time to try to build a DSL for AIR, but it is I think much more complicated than working with R1CS, for example. One advantage that AIR has over R1CS is that you can describe potentially unbounded computations with AIR, meaning once you have this kernel of a kind of repeated computation, you can kind of you're not bounded by how many steps you want to apply it for. I mean, there are some kind of theoretical bounds within a given field, but you can, for practical purposes, say it can be applied for billions and trillions and 2 to the 64 times, whatever. All right. Just to give you another example, so let's talk about let's say Fibonacci function. How would we represent an execution trace of a Fibonacci function? And in this case, let's say we want to use a single column again with 64 steps. So we're going to compute the 64th term of a Fibonacci function. We're going to use a small field to do this. And as I mentioned before, an execution tree is a recording of a records the state of the computation at any given step. So in this case, on the right-hand side, so I have this R representing the step of the state of the computation. So we start with 1, 1 here. Could have started with 0, 1 probably. But in here, we start with 1, 1. And then, our Fibonacci sequence proceeds as usual. We take the previous two terms, add them together, and get the next term. And get the previous two terms, sum them up, and get the next terms, and so forth until we get to the end. This is, again, a very simple computation, and execution trace for a Fibonacci sequence is pretty straightforward to build. If we get to the Fibonacci example, I will show this kind of like, if we get to coding the Fibonacci example toward then, I'll show that this is not the only way to write the Fibonacci sequence using Starks, and this is like where some fun and complexity come into play, where there are many different ways to describe a Fibonacci sequence or an execution trace for a Fibonacci sequence. All right. One of the things that I want to mention about kind of constraints that we think about when we impose constraints on a computation is types of different constraints, and they would be helpful to understand in the context of this ZK hack, because you know, if you try to solve some of the puzzles, this understanding of what is the boundary constraint and what is a transition constraint will come into play. So the first type of constraints is transition constraints. They basically describe algebraic relationships between two or more steps of the computation, or of a computation. So imagine that this is our execution trace. Previously, we had a single column. Now I'm showing here multiple columns, 4 columns to be precise. And these are our steps. And again, here I'm only showing 4 steps, but it could be millions of steps for all practical purposes. So transition constraints, you can think of them as a function that takes you know, 2 nearby rows, but it doesn't have to be limited to 2 nearby rows, but it could be like 3 nearby rows or whatever. But basically 2 nearby rows as inputs, and does some algebraic operations with them, and then produces some value. And we say that the constraint is satisfied if the result is 0. And crucially, we need to describe our constraints in such a way where for every valid transition, the function should output 0, and for every invalid transition, it should output non-zero. So those are 2 important conditions for transition constraint to work. And again, here I'm using just 2 rows. It could be multiple rows as long as they're local. So they have to be local, kind of like you cannot just grab rows from any place in the computation trace. They have to be, let's say, offset by some constant from 1 row, or you know, it should be possible to, looking at a specific row, to just grab the nearby rows and compute this. And nearby could be relative. It could be, you know, 1,000 steps apart, although probably for practical reasons, you may not want to make kind of jumps between rows as big. The other type of constraint, and here, basically when we evaluate these constraints, we apply the same function to every consecutive pair of rows. And this is going to be kind of our constraint evaluation step. I'll show a little bit of this later on. The other type of constraints is boundary constraints. And boundary constraints assert that values at a given cell are equal to some kind of some constant value, something that a prover or verifier wants to assert. So, for example, we may want to say that the first cell in the first row is equal to some value x, and the third cell in the last row is equal to some value y. Boundary constraints are usually used to impose like input and output, or like describe input and output into the computation. Here I'm showing them placed against the first and the last row, but in reality they could be placed against any row, any cell in the trace. They do come at a cost, so you probably want to impose them on as few rows as possible. All right, so this kind of is a very quick, very high-level introduction to Starks. This kind of glosses over a lot of details of the protocol. There is much, much more depth to it, but I hope at least at the high level it provides a quick overview. I'll pause for a second to see if there are any questions. I don't think I'm seeing any. All right, so I'll continue.
Actually, do you want to just Q&A part of the, if you like go on the sessions tab in Q&A, there's a bunch of questions there.
Oh,
yeah.
I should have. Let me see.
You go sessions chat and then Q&A. And I know I added.
Yep, I see it. I see it.
And if you want, I don't know if you want to read them out loud or just if you need to read them.
Yep. All right. So I see the top question right here. Can you explain the cost of a boundary constraint? So the cost of boundary constraints is such that you basically, if you try to impose them in an unstructured way, where you just pick, like, let's say, some random rows in a trace, and you try to impose boundary constraints against those rows, you probably your complexity grows with kind of a linearly with the number of imposed rows, more or less. I mean, there are some caveats to that. So if you just do it this way, you basically transform verification to a linear verification if you have a lot of rows that you want to assert, assert values for. That's why we usually try to keep it minimal. So first and last row is just 2, so basically it doesn't increase the complexity of verification that much. If there are other ways to do it, if you have a repeated value that repeats in cycles that are powers of 2, it's fairly cheap to assert those. But again, if you take just a random number of rows, it's fairly inefficient, and verification complexity becomes linear in the number of rows that you try to assert boundary constraints for. Can you try to explain how these constraints are represented within a Stark? What math is used? I mean, if we think kind of like from a theoretical standpoint, they're just algebraic expressions. They're expressions about polynomials. How you code them up is a different. I mean, in Winterfell you code them up using Rust, and in some cases you may have DSL that could explain, could be used to describe those constraints. But underneath it all, it's still just algebraic expressions of this column in this matrix, or taking a value from this matrix, multiplying from this cell in the matrix, multiplying it by the next value from the same row, a different row, for example, is equal to 0, something like that. So they're just algebraic expressions that need to evaluate to 0 for all valid transitions and non-zero to something that is not valid. Let me see. Please, any simple example that computations of structures might be. So I guess maybe the question is about structured versus unstructured computation. So the simplest or uniform computation. So uniform computation, the simplest form to think, you have something very simple inside a loop and you repeat this many, many times. That's like a very simple uniform computation. An unstructured computation, think about a potential program that has very few loops, a bunch of branching logic. I don't know. There's a lot of nested if-else statements and things like that, and there's really no repeated patterns inside the program. That's an unstructured computation. I think in most cases that we kind of come across it, for a lot of useful use cases, the computations tend to be structured. I mean, it's very infrequently where you would come up with something that is completely unstructured, where you don't make use of loops, or it's all like like a giant like monolith program with a bunch of if-else statements. There are cases like that, I'm sure, but I think those are fairly few. What is field modulus? In this case, as I mentioned, we for all of the proving systems, we work in some sort of finite fields, and finite field is a mathematical concept. In this case, the finite field is a prime field, which means that any kind of algebraic or mathematical operations that happens, we take values, elements from the field. For example, if it's multiplication, we multiply two values, and then we apply the modulus operation by this prime number. So if you think about computer science terms, you will get an overflow if you go above the modulus and you kind of wrap around and come back. The next question is, having the whole execution trace make Stark so large? Not really. It's not really related to the execution trace. I mean, when you generate a proof, having to have like the entire execution trace in memory does impose kind of like performance penalties, because you have to, it would consume a lot of memory. We'll see some benchmarks later on. But as far as the proof size itself, it's not really related to that. It's more related to how the prover like queries this trace, and in the case of Stark, you use Merkle trees, and you need to provide like a Merkle path for every query that you provide, and that's actually what creates a complexity. You can make Stark proofs smaller if you give up some of the properties. For example, if you don't want them to be post-quantum, you can use something else instead of the Merkle tree as a way to commit or to do this querying step. But in that case, you can reduce proof sizes significantly, but you lose post-quantum security. Let's see. I think I might have missed something, but I think I covered everything. If I did miss something, just post it again, and I'll get back to it a little bit later. All right. Oh, I'm not sure what happened. Let me restart this. Can you guys see my screen?
Yep, I think so.
Awesome. Awesome. All right. Oh no. One more time. All right. Let's get into Winterfell right now. So Winterfell is a general purpose Stark proven verifier, and it's written in Rust, and it's open sourced, and it's under MIT license. And what this means is that, so for general purpose, it means that you can describe any arbitrary computation using Winterfell. It is kind of a fairly low level, so it may not be as easy, but you can actually, any Turing complete computation, or you can describe using Winterfell. It's written in Rust, so we get a lot of benefits of using Rust, which is it's very configurable. You can swap out, and I'll cover this maybe a bit later. Hash functions and fields, and without sacrificing performance. And it is fully open sourced, and it's published to Crates.io, so we can start using it. And we will be using it actually for the ZK Mini. So Winterfell is actually not a single library, it's a collection of different components. So there is the verifier and the prover. The prover is used to generate proofs, and the verifier is used to verify proofs, but we also try to break it up into kind of smaller components and modular components that could be used potentially to build other proving systems. So there is the Fry protocol, which is used within Winterfell. It's one of the core sub-protocols within Starks that allows you to test whether a prover committed to something that is a polynomial or not. There is the arithmetization crate that is basically independent from Ref, which allows you to describe error for computations. And then a bit more foundationally, there is kind of the crates that help us use cryptography or algebraic operations that I need to support Stark protocols, such as math and finite fields or FFTs and things like that. And then we also have a fairly extensive crate, which is just has a bunch of examples of how you can use Winterfell to build proofs from something as simple as Fibonacci sequence to something as complicated as verifying thousands of Lamport signatures, for example. Or proving that you verified thousands of Lamport signatures. So there is a lot of things that you can learn just by looking at the examples there. And to highlight just a few key features of Winterfell. So there is I would say, relatively simple interface. So you don't need to understand the full Stark protocol to use it. You do need to understand how arithmetization works. This is non-trivial in itself, but at least you don't need to learn the rest of it. As I mentioned, it's very configurable. You can dynamically select which finite field you want to be in. So right now we have support for 4 or 3 different finite fields within Winterfell, and it's fairly trivial to add more if needed. We have dynamically selectable hash functions. Right now you can choose between SHA-3 and Blake-3, and in the future we'll add something like Poseidon or Rescue, so that you could in theory do this kind of recursive Stark proofs, and then you can fairly easily tune security and do this trade-off between proof size, security, and proving time in real time using kind of just tweaking a few options. And sometimes these are even kind of even runtime parameters. They're not even compile time parameters. And then it's fully multi-threaded, so you can run it on as many cores as they're available. Within some benchmarks, you get about 7x speed up with 8-core machine and 35x speed up with a 64-core machine. And part of it is memory bound, so if you have faster memory, you might be able to even see a bigger speed up. In terms of, I see a question whether security depends on field size. It doesn't depend directly on field size. So you can use a small field like a 32-bit field potentially. You do have to do some extra things, which Winterfell takes care of for you. If you use a small field, for example, Fry protocol needs to be run in a large field. So what you do is you run an extension of a small field for the Fry protocol part. But those are basically taken care of by Winterfell. You can just, from a standpoint of user, you can work in a 64-bit field, and that's all you need to care about. Just to highlight the kind of like overall process of Stark proof generation. Again, not going very deep into this and the parts that are handled by Winterfell. So we have this arithmetization step, which takes a computation or a program and transforms it into a set of statements about polynomials. And then in the next step in the Stark protocol, and this is at a very high level, you do something that is called low degree extension, where you kind of interpret this columns in the execution trace as polynomials or evaluations of some polynomial, and then you kind of like interpolate them and evaluate them over a larger domain. And then next step, you do this constraint evaluations, where you actually evaluate the constraints that we have described as part of our arithmetization. You evaluate them over this extended execution trace. And then you do something called constraint composition. This is basically combining all constraints together into a single polynomial. This is done for kind of efficiency purposes. And then you do this low degree testing, for which you do Fry. We use Fry for that. And then in terms of like which parts of this you as a user of Winterfell need to care about is just the arithmetization part. Everything else is handled by Winterfell. The user needs to provide the description of the computation. All right, some benchmarks here. I'm not going to cover this whole table, so let's just focus on the last row. So basically, this is, as I mentioned, verifying. This is for verifying Lamport plus signatures. So we have a lot of kind of like this signatures that require hashing. So Lamport, for those who don't know, is a very simple hash-based signature. It's a one-time signature where you have a key and you can't reuse the key, if you sign more than once. But it is very robust. For example, it's post-quantum secure, and people usually don't use Lamport signatures because they have fairly large proofs. But if you have something like, if you need to aggregate a lot of signatures, let's say you want to aggregate 1,000 signatures. I don't remember off the top of my head, but if you just had, let's say, raw Lamport plus Lamport signatures, you would get something like megabytes of data. But you can put them together into a single Stark proof, for example, and that becomes much more manageable. So like you can compress signatures in this way, for example, and aggregate them together. And we actually have a paper written about this. In this case, if we have it, and this is running on an 8-core machine, so it takes about 23 seconds to verify 1,024 Lamport signatures. What this basically means is you're, for all practical purposes, just aggregating the signatures together. So like once you verify them, nobody else needs to verify them again. You can say, there is this public keys, and I verified 1,000 signatures, and you can trust me by looking at this proof. And as I mentioned, like verification time is fairly fast. It's about 6 milliseconds for verifying this proof. The proof is fairly large, very large. Not, I wouldn't say very, but it's about 150 kilobytes, and you can flex it. This is for 123-bit security level. So if you wanted to get a higher security level, you would either expend more time or potentially have a larger proof. And then, as I mentioned, one of the I think performance-related kind of downsides of Starks is that you do need to have large amount of RAM available. So in this case, it takes about almost 8 gigabytes of RAM to generate proof. 8 gigabytes is not too bad. Most computers have it, but if you wanted to go beyond that, you can see the RAM requirements grow pretty much linearly with the number of signatures. And in this case, proving time also grows almost linearly. It's quasi-linear, but the proof size, you can see, doesn't change all that much. We increased this manifold, but the proof size increased by less than 50%. I've listed the R1CS equivalent here. It's not a very fair comparison, I would say, because this is an extremely structured computation where you have just basically a loop that verifies a bunch of signatures. So it is more kind of Stark friendly. For R1CS, this would take quite a few constraints to represent. But again, this is not like the type of computation I think that is very well suitable for R1CS. All right. This kind of like covers my overview, and then the next thing would be to work on the post-quantum VDF. I'll do a quick intro, and then we'll do coding of the VDF. Let me see. Do I have how much time do I have at this point? I think I have about 40 minutes, right?
Yep.
All right, so I think we are doing well on time. Let me see if there are any questions.
Yeah, Q&A has a couple more.
Yep.
And actually, folks can upvote other people's questions if they also feel they want them answered.
So first question is, can you use Winterfell to compile a verifier into a smart contract, or how would you integrate this into a Web3 application? So for Winterfell specifically, you would need to write a verifier that can verify Winterfell proofs and solidity or something like that to create a smart contract. So natively, you can just compile it, but it shouldn't be too difficult to use the logic that we have in the verifier in Rust and just write it up in Solidity. In that case, you can verify proofs that Winterfell generates on blockchains. How easy it is to extend Winterfell to support computations in the 256-bit prime field? Would it be slow? So it's not difficult. We just, there is like a set of traits that need to be implemented to support the 56-bit fields. Would it be slow? It would be slower, and it probably, the smaller fields you have, the kind of like, the larger your field is, your complexity is growing faster than linear. So it's not just like if you, let's say, go from 64 to 56-bit fields, it's going to be more than 4 times slower. It's probably going to be closer to like 20 or 30 times slower if you go from 64 to 56-bit field. So it is going to be slower, but it may be acceptable for many use cases. It's not going to be prohibitively slow. Why is it important to have quantum security in the near term? I think it's a more kind of like a philosophical question, whether you wanted to have it or not. I think in the near term and midterm, we probably don't need to be concerned about quantum security. But if we're building systems that we expect to last tens of years, decades, or something like that, maybe it's a bit more, you want to build something that is going to last for a long time. But again, it's more kind of like a philosophical question of, maybe you can augment the system later on as well. In my case, in many cases, you get this post-quantum security with Starks, and because it is using only hash functions, you get other nice benefits like the speed, for example. So one of the things I mentioned, you could make a Stark proof smaller by replacing Merkle trees with some other vector commitments, but it is likely also make lose post-quantum security, but it also most likely going to make proving time slower. So because we need to rely on this very few cryptographic primitives, we get other benefits as well. So post-quantum security by itself, not a huge factor in my opinion, but it's nice to have it if you can get it by getting other things. Let me see. Another question. I'm aware of Plonky 2. Is it the fast when it comes to proving time? But is Winterfell faster than that? We haven't. I mean, first of all, Plonky 2 is extremely fast in recursive context. Winterfell doesn't support recursion yet, so it's difficult to compare, to be honest. And as I said, it's very computation specific. There might be computations that are faster in Winterfell. There might be other computations that are faster in Plonky 2. I think it's difficult to say which one is faster unless you have like a very good set of benchmarks, and even then it's going to be difficult. So I can't really say, especially on the prover side. On the verifier side, I think it's fairly easy, and I think on the verifier side they're fairly comparable. I think in most cases it's just like single milliseconds, but there will be a workshop on Plonky 2, I believe, in a week from now. So might be a good question to ask the authors there as well. But again, I think performance comparisons across these different proving systems and libraries are very difficult. So composability. So another question: composability with Stark. Can you elaborate a little bit on that? How scalable is it in that respect? I think composability with Starks is very difficult, especially like if you think about building standalone libraries of gadgets, for example, that people can reuse. I think that is a fairly complicated challenge, and I don't know if anybody is actually trying to solve that. There is another approach that I think works well for Starks. This is the virtual machines. This will be in the next talk that I give about why virtual machines are useful, and especially in the Stark context. And this is how you kind of address the composability problem, I think. And another question: do you know other tools can generate Stark proofs and can be verified in Solidity? I think there are a couple of limitations of the proving systems out there. I think Starkware, I mean, I know for sure Starkware has a Solidity verifier for the proving systems that they're using. I believe 0x at some point had a Stark prover that I believe had a Solidity verifier as well. So I'm not quite sure if what state those systems are in, and to what extent you can openly use them. But yeah, you can. I mean, you can write a verifier in Solidity. There is no. The verifier is actually fairly simple in terms of what needs to be done. So it shouldn't be too difficult for people who know how to code up in Solidity to write a verifier, a Stark verifier. All right. I think I covered everyone, but if not, do repost your questions. Okay, let's go now to the post-quantum VDF. So first, let's talk about verifiable delay functions. So verifiable delay function is a function that takes some input and produces some output. And we want to have the following properties. We want to, given some input x, we want to compute the output in some time t. And it should be very difficult to reduce t by more than some small, well-known constant. And specifically, you shouldn't be able to apply parallelism, so it doesn't matter how much hardware you throw at it, you can't reduce t by that much. And maybe you can like do some specialized hardware, which could be a little bit faster than generic hardware, but again, it shouldn't be significantly faster. So you can basically just throw resources at it and compute and reduce t by a lot. And then if we have y and x, it should be very easy or fast to verify that y was actually derived from x using f. So this is kind of like we want the complexity to be at least logarithmic, and maybe ideally even constant, but at least polylogarithmic in t. And some optional properties that would be nice to have is that we want to have no trusted setup, for example, and no fancy cryptography to build this VDF. So we're going to build this VDF, and we need the no fancy cryptography part for post-quantumness of this. So in our case, the delay function we can choose could be something like taking a value, raising it to some power, and then adding a constant to it. And again, this is kind of like a toy example, so maybe if you're building a real VDF, this may not be a good approach to do it, but I think this is more kind of to illustrate the point. Let me see. Sorry, not sure why this keeps happening. All right, so if you want to describe this function, this is, you'll notice that this is the same almost example that I used when I described air. You take some seed and number of steps, and you repeatedly apply this power. When we work in finite fields, we can actually run this function in reverse direction, which is a bit more computationally intensive. So, there is like the inverse of alpha, which can be computed in the opposite direction. And depending on which field you use, this could be kind of, you can compute in the reverse direction, maybe at time t, and then in the forward direction, the same thing can be computed maybe in like 1/100th of that time or something like that. But it depends on which field you use. It's the difference is smaller for smaller fields and larger for larger fields. But basically, we have these two options. We're going to use the reverse direction to compute our VDF. So if you think about this, so we apply this VDF function for many, the reverse direction we apply for many number of steps. And on my computer, and actually it should hold roughly true for most general purpose hardware out there, and this would take about 1.7 seconds to compute this function for about 1 million iterations. And then, we could do the naive computation back, as I mentioned. In this case, it's probably going to take, maybe about 100 milliseconds, maybe a bit less actually, to just compute it in a forward direction and verify this. But we want to do something even more sophisticated than that, because the difference between verifying and actually computing is we don't want it to be a constant factor. We want it to be kind of like exponentially faster to verify than it is to compute. And we could use a start proof. So instead of like spending 100 milliseconds on verifying that the function was computed correctly with a start proof, we can do it in 2 or 3 milliseconds. So this is where the start proof comes in. So we will run the function in this direction, and then we'll verify that it was executed correctly using a start proof. All right, some parameters for our computation. So this is the function. This is kind of what we call a transition function for a computation. We'll use this 128-bit field that we have available in Winterfell. This is more kind of, for illustrative purposes. This is not a super performant field. So for production purposes, maybe you would want to use a different field. And obviously, as I said, this is a toy example anyway, so don't use this in production. Our transition constraints are going to be described like this. So we take the kind of the next term and subtract the previous term from it. I'm not sure. Yeah, we can actually describe it in a different way. I think I actually screwed up this definition here, but we'll see the real one once I start coding. And then we want the boundary constraints. We want to start, let's say, this value 5, and then if we run it for about 1 million steps, we should get with this large value at the end. So this is kind of the setting of our VDF and what we want to do. So let's code it up. Let me stop sharing and bring up this. Let me zoom in a little bit. Can everyone see writing fine, or should I zoom in more?
Not so good. I think it should be zoomed in more. And I also know that I think for the video, it's good for when you're doing code stuff to just close, like turn your video off, because then the capture will just be of the screen.
I see. Okay.
But I think, could you zoom a little bit closer? I don't know if other people in the audience have opinions, but to me, it's still pretty small.
Like this?
How about that, guys? I think this is looking good. You can also make it a full screen if you need. And you can hide, to anyone who's curious, you can actually hide the chat if you need to. There's a little arrow near where the number of people here are. Okay, I'll jump off. Go for it.
Sounds good. All right. So here I have like a basic project set up in Visual Studio Code. Just to show what we have here, we just have a single dependency, which is Winterfell, and we're using a concurrent feature to generate proofs concurrently. So fairly bare bones stuff here. So let me see. So the first thing that we want to do is let's start with defining our function. So I have all of this coded up before, so I'm just going to paste some stuff here to save on time. So here's our VDF function. And in this case, let me actually bring in all the imports that I need for this. Felt in this context is just a field element. So a field element in, we're using a 128-bit field available in Winterfell. And then let me bring in some constants that we described in our in the slides out there. So we have our alpha, which is 3. We have this is kind of the inverse alpha, and we have our value 42, which we will be adding. So our function is fairly simple. If you remember, we compute the next state by taking the current state, subtracting the 42 from it, and raising it to inverse alpha. This is kind of our transition function for a given step, and then we apply it for n, whatever number of n is. In our case, n is going to be like 1,000,000 steps, basically. The next thing that we need to define is a set of public how do we think about public inputs into this computation? If you remember to the very beginning of the presentation, I said we have a function. This is our function, and then the proven verifier needs to kind of know the public inputs that go into this. There was also this witness thing that is a secret input. We don't need it for this specific computation, so we only care about public inputs. And in our case, public inputs would be also fairly straightforward. So the public inputs is the value from which we start, the single field element, and then what we get at the end. Even though this is the result, we still kind of aggregate this into something that we call public inputs. And then we need to implement we need to tell the proving system how we can serialize that. So this is kind of like a almost boilerplate of some sorts, but this is just needed to serialize this into this set of bytes. All right. So the next step is more complicated. So we need to actually define air for the computation. So we have the function. Now we need to translate it into air. And within Winterfell, we do this by creating a struct and then implementing air trait on that struct. So in our case, let's call it VDF air. And we'll go into the kind of what goes into this, what we'll actually put into the struct. But for now, let's just implement air for VDF air. To implement the trait, we need to specify a few things. First, we need to specify which is the base field we use for the computation. And this is, in our case, just the field element that we have defined. The other thing that we need is define what shape our public inputs have for the computation. In this case, it will be our VDF inputs. The next thing that we need to implement is we need to tell, the trait requires like a way to instantiate itself, or like the struct to instantiate itself. So we need the new function. In our case, the new function has a specific signature, so the trait imposes this. Trait is, by the way, for those who don't know Rust or not familiar, trait is kind of like an interface. So we need to have this function which takes something called the trace info, public inputs, and options, and these options are really describing the parameter set for the start protocol. So like they say which hash function should be used, which how many queries, and this is kind of the details of the start protocol. But they basically explain or define which parameters we need to use, and those parameters affect like security level of a Stark. They affect the proving time and things like that. So we'll get into some of these parameters a bit later. All right, so there is we'll implement this function in a second. Then there is another function that we want to implement. This is describing how our transition constraints are going to work, and the function is called basically evaluate transition. So this function takes something that is called an evaluation frame, and evaluation frame is basically just a set of two rows. Like there's a current row and the next row. Right now, this is kind of a limitation of Winterfell, where I described, in theory, you could have constraints that span many rows, but within Winterfell, we transition constraints, for at least for now, can only work with two consecutive rows of a trace. So this function takes this evaluation frame, and then it produces the writes values into this result. So once it evaluates the constraints, it writes the result of constraint evaluations into this slice. Slice in Rust context is kind of like an array. You can think about it, or a reference to an array. All right. So the other thing that we need to, the other function that we need to provide is the function defines our boundary constraints. And the boundary constraints in Winterfell are defined by something called assertions. And we'll implement those in a second, but basically this says, specifies what values do we want to assign to a computation in a given cell, for example. And then there is some boilerplate that we need is, a function that returns context of this computation, and this context I'll show you guys how we can do it. So we have kind of stubbed out most of this. So let's go back to our VGF air struct. So we need to return context here, and this is just boilerplate. So for this purposes, we need to just define context here. We also want to keep track of our public inputs within the struct. So we'll just say we have like a seed and result within the VGF air struct. So now when we construct, let me actually not do this first. Let's go here. Let's talk about assertions first. So now we have kind of our struct stubbed out. We have the context implemented, and now we need to actually do the meat part of this computation. So like the assertions, we have two assertions. We want to assert that the initial value of the sequence is equal to seed, and then the last value of the sequence is equal to whatever the result that we're claiming we have gotten after executing the function for 1,000,000 steps or whatever. So we do this by basically, first we want to figure out what the last step is. So we have trace length, and we just do -1 to see which one is the last step. And then we return a vector, and the vector will contain the two assertions that we want to impose. So the first assertion is that it's an assertion against a single cell in a trace, and the cell in the trace is basically this is the index. We only have a single column, so this is going to be 0. This means at the first step, we want to assert that at the first row, in the first column, in the first row of the execution trace, the value of the cell is equal to seed. And then similarly, the second assertion is that in the first column, now because again, the only column, at the last step of the execution trace, the value is equal to result. So this is the kind of boundary constraints. So Winterfell translates these assertions internally into boundary constraints. For our transition constraints, again, our transition constraints are fairly simple. We'll just get the current and the next state from the evaluation frame, and then we have a single boundary constraint, a single transition constraint, sorry. And this transition constraint will basically takes the current state, we take the next state, apply this alpha power to it, and then add 42. So this is, if you remember, like basically this is computing function in the forward direction, but then if we subtract it from the current state, it's kind of like proving that we're proving it backwards. And I should have covered that in the presentation, but we're basically computing the constraint backwards because we can use this property that we're raising to alpha. We actually get a fairly small degree. So this is our transition constraint, and then the only thing left for the air thing is create the actual struct. One of the things that we need to do is create air context. So let me do this. So air context, and I'll just copy and paste to save time. Requires the following parameters. So we need to provide this trace info that we got here. We need to provide this set of options for the Stark protocol, and we also need to provide something called like a description of transition constraint degrees. The concept of degree is fairly important. Like when we impose when we basically come up with these polynomials that describe our constraints, these polynomials have certain degree. If a constraint, for example, uses multiplication, the degree could be, if just one multiplication, 2. If you were using 3 multiplications, the degree could be 3. So we want usually to keep the degree fairly low because it impacts efficiency of generating proof, and also could impact proof size. In our case, if you noticed in our description of constraints, we're raising next to power alpha. Alpha in our case is 3, so our constraint degree is going to be 3. So we need to create this degrees vector that would pass into the context, and this would be, we basically create a transition constraint degree of degree 3. Okay, now that we have context, everything else is fairly straightforward. We just create the struct. Let me just clean this up a little. So we pass the context, we grab the seed from the public inputs, and then we grab the result from the public inputs as well. So now we have described the air for this computation, and I know it's probably, if you've never seen this before, it's probably not super easy to follow. Let me actually see if there are questions. Yeah, so why did I choose to reverse the operation? I think that's a good question and something that I should have explained. The main reason is that, as I mentioned, we want to keep the degree of transition constraints as low as possible. In our, let me see if I have it here. Let me just bring this here. We want to raise it to this huge power here. So like this alpha inverse is a huge power, so our constraint degree is going to be huge. And we can't, it wouldn't be a practical system where we have such large constraint, but we can do it because of these properties where alpha and alpha inverse, we can kind of compute the SIC with both backwards and forwards. We can compute it kind of like if we're computing in a backwards direction, to compute it in the forward direction, we only need to use alpha 3. And this is the property that we're using here, where we set alpha to 3, and we can compute the transition constraints backwards and reduce the power of our transition constraints. That's the primary reason for doing it this way. Another question, do we have to manually calculate and provide degree of the constraints? Yes, you need to do that manually. The library is not smart enough to kind of like analyze Rust code and figure out, how many multiplications you had for a given constraint. There is one way to help you though. If you use a library in debug mode, like if you run your proof in debug mode, when it generates the proof, it will actually check if the constraint that you specified matches the constraint degree that you claim it should have. So in debug mode, it will actually tell you there is something wrong if you define that, if there is a mismatch between the actual degree and the degree that you said it would have. The reason we do it in debug mode only is because this check is fairly expensive, and we do not want to do this check in a release mode. So while you're developing your proof, for example, you run it in debug mode, and it helps you somewhat to make sure that degrees of constraints are aligned, but in release mode, we kind of remove this check so that it runs as quickly as possible. One thing to notice, and I should have mentioned it as well, so as you notice, there is like a single constraint here, and we kind of assume that there is going to be at least one constraint that we can write into. The size of this slice is determined by how many degrees you pass in here. So here we pass the single constraint degree. This means here we're going to be able to write a single constraint. If we had two constraint degrees here, for example, we would have access to two constraints, and we would be able to write into two kind of cells of this result. So, all right. So this now defines the error. So the next thing that we need to do is build a prover. So let's start with the prover that actually will generate the execution trace. So the primary thing for the prover is to generate execution trace. We'll call this BDF prover. I'm just going to copy and paste to save time. And again, it would just take the proof options that describe the parameter. And one of the things that we need to implement for the prover is there is a prover trait. So here we're going to implement the prover trait for VDF prover. And prover trait specifies a few things. I'm again just going to copy and paste. So the first thing, it also needs to specify the field that we're going to use, the base field. It needs to specify which error we're working with, so the error for this prover. So this is going to be the error that we just defined. And it needs to specify what are we going to use to describe the execution trace. In this case, Winterfell provides this trace table struct that you can use as a default trace for probably most of the needs you have. But in case that struct doesn't work for whatever reason, you can always override or implement your own execution trace in whichever way like you need for your specific use case. As before, we have this boilerplate that just returns options of the computation. And then one other thing that we do need to implement here is how do you take a trace and convert it into public input. So in our case, it's fairly simple. In our case, the public inputs are this VDF input and what we get. So get pub inputs basically takes a trace and produces the VDF inputs. And we just take the first row or first column first row as a seed, and the result should be in the same column, but in the last step of the computation. Okay, so this kind of like implements a prover trait. We need a way to instantiate the prover and to build the actual trace. So we'll do another, just implement the specific, not a trait, but just the specific functions for this struct. And we want to have a new function that creates the prover. And then there is going to be this the function where the real work happens. This is the building of the trace. And again, in our case, this is relatively simple. Our trace consists of just a single column. So we'll just use this vector to contain the values of this column. And then at the end, once we've done building it, we'll just initialize our trace table with this column. So it will pass it as a, in theory, like if you had multiple columns, you would be able to pass multiple columns here. But in our case, we just have one column. And then the way we're going to do this is that we're going to initialize the state of our computation. So here's the state is just going to be a single field element. And we'll start by pushing this field element into our trace. So this is going to initialize a trace with the first step of the state of the computation. And then we're just going to repeat this for n minus 1 number of steps in this case. And if you notice here, we're running the function in the reverse direction here. So we're raising to inverse power of alpha. while when we do the transition constraints, we verify it using the just alpha itself. So if you remember, inverse alpha is a huge degree, but alpha is just 3. And then once we update the state, we again record the state in the trace. And then by the end of this loop, we have our full execution trace built. All right. So the last thing that remains here is let's build the main function. So we want to run this for like 1,000,000 steps, and we want to start with value 5. So this is our initial inputs. Just for kind of sanity checking, making sure that we did everything correctly, we're going to run this computation separately using our VDF function. So in theory, this is not required if we do everything correctly, because we'll get the result by building an execution trace. But here, just to see how long it takes to compute the VDF, we can, without building a trace, we can just run it separately and get the result and see if we actually coded things up correctly. The next thing we need to do is we need to define the parameters for our start proof. So this is the option object that I've been passing everywhere. So in here, there are a few things that we need to specify. I don't think I'll have the time to go into all of them, but there is documentation here that describes all the parameters and their meanings and so forth. But basically, we want to have this is number of queries that determine the security level. This is blow-up factor that also determines security level, as well as how long the prover will run. Grinding factor that kind of allows you to increase security at the expense of the, prover time. Hash functions and extension fields that we're going to use, and then some Fry-related parameters as well. So once we have this, we are ready to instantiate our prover. And this is just very simple to do using the new function that we defined before. Again, we pass our start parameters to say, for the prover to be aware of the parameters for the protocol. And the next thing that we want to do is build an execution trace using this prover. So yeah, this is what we do here actually. We build the trace using the build trace function that we implemented, and here we just record how long it took, and also make sure that this result is the same as the result we got here. Again, this check is only for our sanity to make sure that we didn't screw anything up. Let's see. So the next step that we need to do is generate the proof. So once we have the prover and we have our execution trace, we need to generate the proof. And we do this simply by saying prover.proof, and we pass in our trace. And this generates the proof of our computation. It is as simple as that at this point. I mean, there's been a lot of work to actually write up the error and stuff like that, but now that we have the error defined, generating a proof for this computation is just as simple as passing the trace and saying proof. We want to, just for informational purposes, figure out how big the proof is and print it out. So we just serialize it here and see what security level we get. And then let's see, we want to again deserialize the proof to make sure that serialization and deserialization works fine. And here we would see that if we serialized and deserialized proof should be the same. And the last thing that we want to do in here is just make sure that the proof actually can be verified. So here is the simple set of statements. Let me explain this. But basically, we're just saying Winterfell verify. We specify which error we're using to verify a proof, and then we just pass in. Well, one thing I forgot, we also need to build public inputs. So in this case, we here want to build public inputs. In our case, the public inputs is just seed and result. So given the seed and result, we can say whether this proof, so for this public inputs, the verifier should only accept the proofs that are valid, meaning we ran the computation specified by this VDF error. We started with seed and we ended up with result. And this is the proof attesting to that. So this is the whole thing. And let's see how it works. So it's going to compile. All right, so what do we get from this? First, it ran about, the actually running the computation took about 1.7 seconds, which is what I was aiming at. Executing this function for 1 million steps takes about 1.7 seconds. Building execution trace is basically the same as computing the function. There's really no overhead. It actually, for whatever reason, came out a bit faster, probably for some idiosyncratic reasons. It should be basically the same. Generating the proof here took about the same time as running the VDF itself, but this has been spread across, I have 10 cores on this machine, so across 10 cores. If we did on a single core, this would take probably close to 20 seconds, I want to say, maybe a bit more. And if we had 16 cores, obviously it would be roughly half that, maybe a bit less than half. So you can actually verify and generate a proof faster than it takes you to run the VDF. And if you have more cores available, it could be 10 times faster or maybe 20 times faster to generate the proof that as compared to running the VDF itself. Proof size in this case is 114 kilobytes. Our target security level is 100 bits. And verification, crucially, this is what we were trying to do. This is why we bothered with the Stark in the first place, is just 1.7 milliseconds. So we ran the function for 1.7 seconds. We spent about 1.7 seconds on generating the proof, but then verifying it cost us just 1.7 milliseconds, so 1,000 times faster. All right, this kind of like it concludes the coding portion of this. Let me see if you guys have any questions. All right, I don't see any questions, so either I confused everyone or everybody understood everything.
Thank you so much, Bobbin, for this great workshop.
Yeah, happy to do it. And if there are any other questions or follow-ups, always feel free to post them. We'll be happy to answer them.
Cool. So yeah, our